Welcome to Hot Topics. Today's subject, we're going to deal with short circuit current. What is short circuit current? What is ground fault current? What's a grounded conductor? What's a neutral conductor? What is GFCI protection? What is AFCI protection? Now, we can get all of that in one breaker now. We get all of that protection in one device, circuit breaker, if that's our desire. But we've had questions come in and wanting to know the difference. So we're going to kind of talk about that in this video. But notice we're going to use this illustration from Stallcup's Electrical Design Book, Volume 2, Chapter 16, that deals with grounding and short circuit current, ground faults, etc. Now, notice what the plan is here. It's to size a grounded conductor from this earth grounded bar back to the transformer and return on the phase that is short-circuited and open up the overcurrent device in a localized area so you don't knock out the whole service. It has to be designed right. But to design this grounded conductor from the transformer, you have to decide, is it a neutral or is it just a grounded conductor? Now, when we review these definitions, we'll get a little bit better handle on this. But notice, are we developing a short circuit here or a ground fault? A ground fault would naturally be from the hot conductor to the metal enclosure enclosing the conductors or the equipment enclosure, and it returns back to the grounded point of the grounded bar that you see in the service equipment here. Now, it has to be sized, if it's an equipment grounding conductor now, based upon the size of the overcurrent protection device in accordance with Table 250.122. Now, so if you had, say, a 30 amp overcurrent device here, you'd need a number 10 equipment ground if you pull one and you conduit. If it's a non-metallic conduit, then 250.118 of the code says you have to have an equipment ground. If it's a metal conduit, you have a choice, or a metal raceway. In accordance with 250.118, the metal, if installed properly, all couplings tighten, connectors, threaded couplings, whatever it may be, then it can serve. But most engineers that I talk to today and do work with, they pull an equipment ground and everything. They say, if we start getting corrosion, loose connections, or whatever, we'll have two paths. We'll have the metal raceway path, if that's what we're using, and the equipment ground. But we know from our experience when we review, say, SOAR's grounding book, our grounding book, or the IEEE Green Book, that the equipment ground will pull about 10% of the ground fault, but the metal conduit will pull about 90% of that fault. But if you should develop a restriction somewhere in that raceway run, then that equipment ground will pick it up. You'd say, well, what do you mean? Say at a connector somewhere, and we're just saying this, that a resistant developed due to loose connections, not tightened couplings or whatever, or punched out rings, broke loose, whatever, and say that the metal conduit would only pull 70% of the fault, then the equipment ground would pull 30%. But we size it from Table 250.122 based upon the overcurrent device ahead of the ungrounded conductors. And then we would develop and select our grounding scheme from 250.118 of the code, and then we would color code it or identify the equipment ground in accordance with 250.119. But I suggest to people that, and installers and designers and maintenance people, I suggest that you always keep a note in your code book of 310.10 and 310.10, because those sections will deal with insulation. You can install that insulation in damp or wet locations or exposed to the sun. It'll refer you automatically to 200.6 to identify or color code the neutral or grounded conductor. 310.10 will also, I think, refer you over to 250.119 to color code or identify your equipment ground. It'll also refer you over to size your ungrounded conductors. Not necessarily size them, but color code or identify them in accordance, with the branch circuit or a feeder. Now, looking at this grounded conductor here, we want to see if we want to use it as a neutral or grounded conductor. Again, NFPA 70B for fuses, Chapter 18, for circuit breakers, Chapter 17, and the Annex L to 70B in the back of the 70B document, kind of says, look at your circuit mapping. If this panel is just supplying more phase-to-phase loads without neutrals, then this neutral might be too small. As a young designer, I made that mistake at a welding shop. I just sized that neutral for the calculated load and was going to, just do that. And that, that was 220-22 in those days. And, the maintenance people were pulling in a branch circuit and used a metal fish tape and got it into the bus bar and metal enclosure, created a ground fault, but I didn't size that in those days by my table 250.94, or it's dash 250-94, and it was too small. I was really lucky. It only damaged the neutral bar, and it'd been a federal type panel. I didn't damage any of the ungrounded the bus bars or the conductors there. Just that neutral, I'd kind of whipped up on it. And we just had them change it out and put in a larger one, see. But I goofed up there because I didn't take 2 steps. You have to design by 220.61. For example, I might have, say, a 3-aught feeding this panel board with a 200 amp main. I may have a 4-aught conductor from table 310.16 supplying a 225 amp main. And I have to check it to see if there's more phase-to-phase loads without neutrals, or is there more phase-to-phase loads with neutral connections. And that's what 70B tells us. That's one way to check your circuit mapping, is one way if it's naturally, if it's been identified properly. Now, 220.61 would size the neutral. And if my neutral came up to 1-aught and say 4-aught ungrounded conductors supplying the 225 amp main, then I'd go to this table you see here, table 250.102C1, and size it for fault current. And if you had 4-aught here, it would be a number 2. So the 1-aught would be used by 220.61 because it's the largest. But if you had a lot of phase-to-phase loads here, then 70B, naturally is referring you back over to the NEC. And of course, you can find this in Chapter 7 too of 70B, NFPA 70B, the maintenance standard. Then notice that if this was number 6, calculated neutral load by 220.61, too small, because 250.102C1 here requires it to be number 2 based upon the size of these conductors. Now, remember that your table 250.102C1 deals with this grounded conductor, supply side bonding jumpers, the system bonding jumper. It happens to be a conductor. It deals with that and tells you how to size those. And the information pertaining to each one of these components is listed in the head of the table 250.102C1. But if you're sizing these grounding electrode conductors, then that would be table 250.66. And just for your information and anybody's, table 250.102C as in car 1 is an overlay of table 250.66, but we're using the right terms. IEEE and the engineers said, why are you sending us to table 250.66 to make sure this grounded conductor is large enough to serve as fault current when table 250.66 just deals with grounding electrode conductors? So that's why this table was created. Table 250.102C1 is to deal with the other items of these that pertaining to these conductors that wasn't grounding electrode conductors, but supply side conductors in some manner. So yes, we need a number 2, see, routed up here. Usually this is a number 6, and this could be sized, from table 250.66 for a water pipe or structural steel. But this driven rod now, you would have to go to 250.66A is an apple to size it. So we only use our table 250.66 basically when we're connecting the grounding electrode conductor to a metal water pipe that serves as an electrode, or it's not an electrode because we're coming in maybe with a polybutylene or some non-metallic system for the water. But if it's all metal, then it is an electrode of 10 feet or more if it's in the earth. See, we know that. But now getting back now to the other thing I might point out to you. You see where these systems are here, that'd be 5 ohms, 5 ohms here, 10 ohms into 277, 480 volt. You divide the 10 ohms into 277, it's about 28 amps that would work its way through this earth back to here. That's why this grounded conductor has to be large enough, see, to carry your fault current. And if you had a 120, 240, 120, 208 volt system, divide 10 ohms, 5 ohms here and 5 ohms here, into 120, you only have 12 amps basically working there. And that is an excellent rule of thumb. Instead of you having to measure all that with a 4 earth ground megas. See? Now, but when we get into our short circuit current, you go to page 35 of Article 100. And on page 35, short circuit current is defined. And this is what kind of some of our folks get mixed up on. And I'm not saying you do now, but some folks do. They'll say, well, the neutral conductor will go back here and connect to earth ground. So why is it considered a short circuit? Because when we short out from the ungrounded to we get maximum fault current. But if we go to ground, if we're not sizing that equipment ground in raceways properly, then you don't get maybe enough current in some instances to open up that overcurrent device. So that's why engineers and electricians are being more careful when they run a metal raceway, that they go ahead and pull an equipment ground too, and then they have a redundant grounding system. So that's the difference. And then notice if you're an equipment ground, you're in parallel. You're connected to earth ground here, but you're connected to the metal here, where the neutral is prohibited to be connected there when you look at 200 2.6 and go through that series of where the neutral cannot be connected to metal on the load side of the service. It's just where it's earth grounded. So that's why it's a short circuit from an ungrounded conductor to an ungrounded conductor, or from an ungrounded conductor, hot conductor, sometimes you call it, to the neutral. But a ground fault is when it's the ungrounded conductor, hot conductor, to metal. That is considered a ground fault. Now notice you can pick that up on page 35 for both of them. But the grounded conductor, and you say, well, what is that? Well, say that this transformer, we're just saying this now, is 480 277, but when you bring the 480 and 277 in, it's only equipment, 480. A lot of times people say, well, I don't have no neutral. I don't have a 277 volt neutral. And sometimes they'll just leave that neutral out. And we're finding that today, and it shouldn't happen. But where people are installing this equipment they have not had the experience and the time to learn these things. Why it becomes a grounded conductor then? Swear, table 250.102C1. Has nothing to do with the neutral current, because we're going to set a main and install a main and feed a transformer, 480 volt, 3-wire primary, and step it down to 122.08 maybe for our 120 volt loads, because we don't have any neutral loads at 277 at all. So keep that in mind when you're reviewing the short circuit current, the ground fault. And then if we want to pick up, say, the grounded conductor and define it, we go to Article 100 and the informational node. Now that's on page 36 of your NEC. And basically, the grounded conductor is not a neutral conductor. It is not an equipment grounding conductor, and we find that information in the informational node to Article 100 for the definition of a grounded conductor on page 36 of your code book. Now, the next thing we get into is the definition of a neutral. And we go to page 38 of Article 100, and the neutral is defined. And the neutral is a different conductor than the grounded conductor. The grounded conductor, size from 250.102C1, is for ground fault return path. We know that by 250.4A5 of the code will tell you that. So we know that. So the neutral now, it's a grounded conductor, but it's a neutral now because you have neutral load. And we have to size it by 220.61, as I just previously pointed out to you. So page 38 defines the neutral and the neutral point, which is back here at the transformer. That's your neutral point. Now, GFCI protection, then you know that's for personnel. Safer dwelling is 210.8 A, and if it happens to be in a commercial or industrial location, then it's 210.8 B as in boy. So we look up those sections, and we find every location in a dwelling unit in 210.8A that GFCI protection is required. 210.8B deals with other locations and other facilities and occupancy, such as commercial and industrial. But we know that it's 5 milliamp plus 1 or minus 1. So we could go up to 6 milliamps. Then it's going to open up if we should have current flowing through our bodies to ground. And then that's what the definition defines it there on page 36, I believe it is. Now, AFCI protection is short, it's low magnitude faults, like for extension cords, cords that supply lamps and things like that. Now, we would go to 220.12 to make that installation. Now, I'm finding in most inspections that we make that they put in a circuit breaker that has short circuit, ground fault, overloads, protection, but also has GFCI and AFCI all in one breaker, and they just put that in their panel board, see, and use that for those outlets that are required to have AFCI and GFCI protection. When you see where this protection is required in the code. Now you can go over to page 32 and it'll define what your AFCI protection is and all about. But you go to 220.12 to make the installation of a AFCI type protective scheme. Now, you pretty well have it. Now, your overloads, you can go to Article 100, and an overload is simply, in school, I never will forget this. This kid down on the front row, he gave the old professor a hard time, the instructor and teacher. And he said, I understood perfectly overcurrent protection, overloads, and all that till you started today. Now, back then, remember, we only had ground fault protection, short circuit current, and overload protection. That's all. And he took a piece of wire out, about a foot long, insulated, but skin on each end. And he gave it to this kid, and he said, now you hold this. And he took a cigarette lighter and started heating up that copper. Now he said, hold it, with your thumb and your finger long as you can. And in a minute, that kid, did like that and turned it loose. And he said, son, that's an overload. It's a slow heat buildup of an overloaded system that's overloading the wire, and it heats up the copper. The overload characteristic, sized at 125% of the circuit breaker, picks it up and opens it up. And then he just hauled off, boy, and he slapped him across the face, and man, it popped. Now he said, that's a short circuit or a ground fault. And he said, in a minute, your eyes are going to focus, the tears will be out of your eyes, you'll reset, and you can see perfectly, and you can operate and see your vision will be good again. Now he said, you understand the difference now between an overload, short circuit, or ground fault. And that kid said, oh, hell yes. He said, I got it. Well, I'm sitting back there, and I got it too at this kid's expense. But he shut that kid up for the rest of the semester. He didn't mouth off at the instructor anymore. But that's basically what we're talking about here. What is the difference between short circuit, ground fault, grounded conductor, neutral conductor, AFCI protection, and GFCI protection, and how they are related in the electrical system? I hope you enjoyed this video, and I hope that some of this terminology now straightened out. Now notice in the illustration you have a lot of references there for case study. You don't have to reference them. This is strictly dealing with short circuit current, neutral and grounded conductor, as we've just kind of pointed out to you. So take good care of yourself, and may the good Lord take a liking to all of us.